Any shape you can draw with a pen on a paper can be built by adding up a lot of sine waves. Literally any shape at all. This is the idea behind Fourier series and Fourier Transforms, named after Joseph Fourier. And without it, you wouldn't be able to watch this video or send a voice message or even take pictures on your phone. Not only does this idea power Wi-Fi, radar, MRI, you name it, but about a century ago, it helped power the British Empire's global sea trade. And decades later, it decided the date of the largest seaborne invasion in human history. But why is this true in the first place? And how does that help my phone take pictures? And where did it all come from? I never thought I'll get any intuition behind this until now. Fourier says all of this, every single aspect of it, including all the math, can be rediscovered from just one fact, that heat flows from hot region to a cold region. That's it. Nothing else. Wait, what? What? How does this lead to what? Fourier says, Mahesh, here's a hot piece of metal. It's touching a colder one. What happens to its temperature? Well, heat flows from hot to cold, so its temperature is going to reduce, obviously. Fourier says, wrong. Why? Because it's also touching a hotter piece on the right with the exact same temperature difference. So the same amount of heat flows back in, making the net heat flow 0, so our temperature remains unchanged. Fourier, you tricked me. What's your point? The point is, if the left piece was only slightly colder, then look, the amount of heat flowing out would be lesser, and now the temperature of our piece will increase. Makes sense? And if this hot piece was even hotter, then the temperature is going to increase faster. Yeah, that also makes sense. So the question is, what decides how quickly does the temperature of our piece change? What decides the rate of change of temperature? Well, I know that it's got something to do with the difference in temperature, but I can't put my finger on it exactly. Fourier says, no worries, think geometrically. So let's go back to our first case and draw the temperature position graph. Remember, the temperature was unchanged over here. What does the graph look like? Well, since the temperature difference is the same, the graph is going to be a straight line. In other words, the slope of that graph is unchanged as I go from here to here. And when the slope is unchanged, the temperature is unchanged. Ooh, is that a coincidence? Let's see. In the second case, this piece was only slightly colder. And so now as I move from here to here, the slope increases and the temperature also increases. And in the third case, this piece was even hotter, which means the slope increases faster as I go from here to here, and the temperature also increases faster. So there is a nice correlation between this. We see the rate of change of temperature is directly related to how quickly the slope changes, the rate of change of slope itself. But slope itself is rate of change of temperature, so we get a second derivative. And there we have it, the legendary heat equation. Okay, but what is this equation telling us, and why is it so legendary? Well, the second derivative means a curvature. So how quickly the temperature changes at a spot depends on the temperature curvature at that spot. For example, if there is no curvature, the temperature is unchanged. If there is a positive upward curvature, look, the temperature increases at that point. If that curvature is stronger, the temperature increases faster. And of course, if there's a downward curvature, the temperature would reduce. Now, let's put this into action. Suppose we have a rod sitting here at room temperature. We heat up one specific spot, so the temperature spikes over there. The question is, what happens a little while later? How do we figure that out? Well, just look at the curvature everywhere. At the peak, the curvature is the strongest, so that is the point where it will cool down the fastest. As we go farther away, the curvature reduces, and then the curvature goes to 0, and then the curvature becomes upward, and so these spots actually warm up. So a little later, our profile is going to look like this. This equation allows us to predict what happens to the temperature profile. It helps us understand how the profile evolves over time. That's awesome. But I still don't get why this is so legendary. Just like how heat moves from high temperature to low temperature, charges inside a neuron, for example, move from high voltage to low voltage. Which means the exact same physics can be used to model how electricity flows through a neuron. All we need to do is replace temperature with voltage. That's awesome, right? And the exact same equation governs how mutations spread through a population or how uncertainty spreads through financial markets. Oh my God! Why does this single equation work everywhere? Because at the heart of it, the central phenomena is diffusion. So this equation is fundamentally a diffusion equation. It's one of the most common things that happen in our universe. That's why this equation is legendary. And we derived it from scratch, just from the fact that heat moves from hot to cold. That's awesome, right? Okay, but what does this have anything to do with Fourier series? Everything, because now we have a big challenge in front of us. How do we actually solve this equation? I mean, so far we solved it qualitatively, looking at it step by step, but how do we get a mathematical expression for it? Solving differential equations are not easy. So what do we do? Fourier uses one of the best problem-solving techniques. If you can't solve a hard problem, see if you can tackle an easier version of the problem. Okay, what's the easier version of the problem here? Well, here, if you look at the initial profile, the curvature is all over the place, and that's why things look complicated. So can we start with a profile whose curvature is nice? Yes. What about a sine wave? How on earth does sine make things easier? Well, Fourier says sine has a beautiful property. Its curvature is proportional to the height. What does that mean? Well, if you look at this point, the height is 0, right? Guess what? The curvature is also 0. This is the point where the height is maximum and the curvature is also maximum. If you consider a point where the height is half the maximum height, the curvature at that point is also half the maximum curvature. See, curvature is proportional to the height. Okay, so this means if the starting profile was a sine curve, then the rate of change of temperature is going to be proportional to the height. Which means the temperature at every point changes in proportion to its height. And so a little while later, the shape looks exactly the same. Sine just shrunk down. That is cool, right? And that continues forever and ever. And the whole point is that is super easy to write down. The whole graph is just shrinking exponentially. So how can we mathematically write down? Well, we can say the temperature profile is basically the sine graph whose amplitude shrinks exponentially. So this part stays the same because the graph stays the same, the shape stays the same, and this part represents the whole graph shrinking exponentially. So if the initial graph is a sine curve, look, this is the exact equation that represents this evolution. That's awesome. Okay. Now here's a question. What if the initial graph had two sine curves? This also behaves the same way, but the question is, will it shrink at the same rate as the previous one? Will it shrink faster or slower? Why don't you pause the video and think about it? Well, now we have squeezed two sine waves in that same place as before. And so now the curvature everywhere is much higher, right? We can visually see it. So the temperature change is going to be much quicker. The whole graph is going to shrink much faster than before. Higher the frequency, the faster it shrinks. Makes sense, right? Okay, this is great, but Fourier, what's the point? I mean, this would only work if the initial profile just happens to be a sine curve. The real world profiles are not sine curves. So what can we do with that? Well, Fourier asks, what if we had the initial profile which was sum of two sine curves of different frequencies? the result will no longer be a sine curve. Its shape will look pretty complicated, right? Now, if you try to solve how it will evolve directly, that would be a nightmare. But we don't have to. We can split it back into its component sine curves. And the whole point is we already know exactly how each one evolves. The high frequency ones die out much faster, right? And so then what we do is we simply add them back together to get our final profile. Oh my God! That is amazing. So the trick is we never solve a complicated graph directly. Instead, we just break it down into its component sine waves, let each one evolve over time because we know the exact math for that, and then stitch them back together. That is so ingenious. This works because derivatives are linear operators, meaning derivative of a plus b equals derivative of a plus derivative of b. But again, Fourier, this only works provided the initial profile just happens to be a sum of two or more sine waves, right? What if it's not? And Fourier makes an incredible leap at this point. He asks, what if this is always true? What if any graph or any shape that you can draw with a pen and paper can be broken down or can be built by adding lots and lots of sine waves? Then the heat equation would be officially solved because you can use the same technique to solve any shape. This is the birth of Fourier series. Here it is. Fourier's intuition is kind of like a mathematical prism. Just like how a prism splits light into its constituent colors, Fourier asserts that any shape can be split into its constituent sine curves. This means we can transform any shape into a graph showing the strength of those constituent frequencies. Today we call this graph the Fourier transform because we are literally transforming this graph into the frequency domain. But Fourier, right now, this is just a fantastic idea. I know we want it to be true, but how do we know that this is indeed true and not just wishful thinking? Fourier says, Manish, the only way to trust ideas as wild as these is to try and build it ourselves from scratch. Just like how we do with Brilliant, the sponsor of this video. The biggest frustration I heard from parents when I was a classroom teacher was that their kids don't get individual attentions. I mean, how could they? Even the best teachers can only do so much when you have 40 or 50 people in a classroom, right? This is where Brilliant comes in. Just check this out. Koji, I have no idea what to do over here. Can you help?
You're getting the doubling right. But how many people
This is Koji, Brilliant's AI tutor. It doesn't just give answers, but actually walks you through the steps like how a real tutor would do.
You said it doubles, but then multiplied by 3.
And what if we had 4 people who knew the joke on day 0 and it tripled every day? And look, you can even ask what if questions, just like how you would do with a real tutor.
Yes, that's exactly right. You've got the pattern down.
Okay, this makes sense. Brilliant is using AI to make personalized tutoring quite affordable. They have a bunch of courses in math, programming, science, and technology across various grade levels. And what's even better is you don't even have to take my word for it. You can try it out for free using the link brilliant.org/FloatHeadPhysics. The link is also in the description, or you can just scan the QR code. And if you do decide to make a purchase, you will also get a 20% off on the annual subscription. So happy learning. Back to the video. So Fourier, how do we actually prove that any shape can indeed be built using sine curves? Well, for any given shape, we just need to know what frequencies make it up and what the height of those frequencies are. Then we just add them up and check if it gives us the right shape. We can add them up just by using pen and paper, or we could use machines to do it, or we can just put it in a simulator. But how do we figure out their constituent frequencies and the heights that make them up? I don't even know where to begin. Fourier says, let's assume that our signal repeats forever with a period t. Then finding the frequencies is very easy, he says. Wait. why are you assuming that our signal is periodic and repeats forever? It's not. And if it did, why would figuring out frequencies would be easy? I don't get it. Fourier says, remember Mahesh, how when you're stuck with a hard problem, you need to first see if you can solve an easier version of that problem. Periodic signals are much easier to solve. So that's why let's start with that. Okay, but how does making it periodic make it easy? Here's how. If a signal keeps repeating after a period t, for example, then any sine wave that contributes must also repeat perfectly after period t. This means we can have a sine wave that completes exactly one cycle, then it'll perfectly repeat, or 2 cycles, again it'll perfectly repeat, or 3, and so on and so forth. But we cannot have anything in between like these because they won't perfectly repeat. So they won't perfectly line up. Okay, that's pretty ingenious. And by the way, there's also a zero frequency term, a constant function. Wait, why? It simply tells us how much the whole signal is shifted above or below the zero. So look, by assuming periodicity, we have easily figured out the exact frequency constituents. But now comes the main question. How do we figure out the exact heights of those constituents? Fourier says, easy, algebra. Okay, what? Let's call our shape f of t. Then we can write this series as a summation. Now, if you have one unknown, you need one equation to solve it. If you have 2 unknowns, you need 2 equations to solve it. Here we have infinite unknowns, so we just need infinite equations to solve it. That's it. Oh, okay, that's it. Fourier, we just have one equation. Fourier says, no, I see infinite equations. How? Differentiate. If you differentiate this equation, you will get another equation. And the thing is, sine and cos are infinitely differentiable. So I can just keep differentiating this over and over again. I'll get infinite equations. Now I just have to solve these infinite equations for my infinite variables simultaneously. Madman! You're a madman! No man, physicist or mathematician, threatens a learner with infinite equations. I'm done. I quit. Fourier agrees. This is absolutely ridiculous. We need to find a better way to go about it. So if we can't differentiate, maybe we can try integrating. That's it! Integration! That is the key! And I say, stop, Fourier, stop doing that thing where you get things instantly and I don't, and you have to spell it out for me. Fourier asks, what exactly is an integral? Well, I know integrals are basically calculating area under a curve. Right. And integrals are also linear. That means the area under this curve equals area under this plus area under this plus area under this and so on and so forth. Right? Yeah. But look at the sine curves. Over a full period, their positive and negative areas perfectly cancel out. So they all disappear. That means the only survivor is this one. So the area under our curve is exactly equal to the area of this rectangle, which is basically the height times the width t. And so we can now write h naught times t, the area of this rectangle, equals the area under this curve. And from this, we can isolate h naught. We have found the value of h naught. It's the area under the curve divided by t. That's pretty cool. That's how integrals can help us. Okay, I admit that's cool. But how are we going to find the values of h1, h2, h3, and so forth now? So this time, we want to do something similar, but this time we want to isolate h1. So the question is, can we do some operation on this entire equation such that when we calculate the areas, only h1 survives and everything else cancels out? Okay, so the problem is for h1, the areas are positive and negative that cancels out. We don't want that. We want the area to be just positive. For example, we want this to flip over and become positive. How do we do? I got it. I got it. Square. Because when you square something, the thing becomes positive, and so we'll end up with positive areas. So we have to square it, Fourier, right? And Fourier says, you're on the right track, Mahesh. But the problem is when you square, everything gets squared. And so everything will become positive. Nothing will cancel out. Also, squares are not linear, so that's an additional problem. Okay, so what we need is some operation that only squares this one, but doesn't square the rest, and it should be linear. What kind of an operation would that be? Fourier says, simple. Just multiply the whole equation with sine. When you do that, look, this gets squared, but the rest don't. And sine multiplication is linear. So because this got squared, this will now end up with a positive area. Okay, but what about the rest? What happens to them? Will these cancel? To think about the areas, think about the product. If they both have the same signs, then the product is going to be positive, and so the area will also be a positive. But if they have opposite signs, then the product will be negative, and the area under the curve will also end up becoming negative. Okay, what happens here? Over a positive half cycle, we have the same sign. Both are positive, so you get a positive area. But over the negative half cycle, you have a negative times positive, so the product becomes negative. So you get an equal negative area. So this time, this cancels out. Okay, what happens here? Notice over a positive cycle, you have a positive and a negative area. But over a negative cycle, the whole thing reverses. And so again, it perfectly cancels out. And the same thing applies everywhere. So indeed, these all cancel out. And we are left with H1. Oh my God, this is working. But Fourier, there's a small problem. We need to now find the area under this curve. That's going to be hard to do, right? And Fourier says, actually, Mahesh, it's going to be super easy. Barely an inconvenience. What? How? I'm embarrassed. I'm sorry. I'm embarrassed. Okay. Anyways, so we now need to find the area of this rectangle, which is just the height times half of the period. So now we can say h1 times t over 2 should equal the area not under ft, but ft times the sine. This is how we isolate h1. And now we can do the same thing for h2. Multiply the whole thing with that particular sine curve, and then calculate the area here. And we'll find that this area remains positive where everything else cancels out. And then to find the area under this curve, we do the same trick that we did before. And notice h2 times t2 now equals area under this curve times the sine. This is it. Okay, why did this work? The general idea is when you multiply two sine curves, if they perfectly line up with matching frequencies, then you'll end up with a positive area under the curve. But if their frequencies don't match, they will not line up perfectly. They will go in and out of alignment. And when that happens, the area under a curve and over a full period will be 0. So that's how you can use each sine frequency as a probe to calculate its strength. It's kind of like using a filter to find the strength of a specific color that you're looking for. That is so cool. So this is it. We now know which frequencies and what the height of those frequencies are. We can calculate it and we can put it back together and we can check if this is indeed true. So Fourier says we are almost done now. And I'm like, wait, what? Why do you say almost? We are done, right? Well, there is one small subtlety. Well, so far we assumed that every single component starts with this exact phase. But what if it doesn't start this way? What if the graph is shifted like this, say by a quarter of a cycle? Now, if we were to multiply by sine, then look at what happens. They will not be aligned. Now you will get positives and negative areas, and they will perfectly cancel to give the area under it to be 0. So if you did this, we might wrongly think that the height of that frequency is 0. But that's wrong. It exists. It's just that it is phase shifted by a quarter of a cycle. So how do we take care of this? Fourier says simple. A quarter of a cycle phase shift is basically cos. So this time we should have actually multiplied by cos and calculated the area. That would have given you the correct answer. But Fourier, how do I know beforehand whether I should be multiplying with sine or a cos? Fourier says, good point. Do both. What? Yeah. If you multiply by sine and you get, say, the height to be 0, then you know the height from the cos is the real height. In contrast, if the height from the cos gives you 0 answer, then you know the height that you calculated from the sine is the correct answer. But what if it's not shifted exactly 90 degrees? What if it's shifted somewhere in between? Then both sine and cos will give you some non-zero answers. Now what do we do? Well, now we just use the Pythagoras theorem to get the real heights. Why Pythagoras? Well, because when you multiply by sine and cos, what you're really doing is calculating the two perpendicular components. So you use the Pythagoras to calculate the full height. And if you take their ratios, you can now calculate the phase angle, and that will tell you exactly how that graph is shifted. So for example, if that phase angle is 0, then you know that it's shifted by 0 degrees. It's a perfect sine. If that phase angle is 90, then I know it's shifted by a quarter of a cycle, and so on and so forth. So now by calculating both the sine and cos, we have the full picture. We now know both the heights and the exact phase shift of the constituent graphs. This tells us the exact heights, and this tells us the exact phase shift, and now we are perfectly done. And so now if we account for the phase shift, we are done. So in its full glory, the Fourier wait, says Fourier. Let's first clean this up. First, let's write this down as a summation where n is an integer. Then we turn the areas into integrals over a period, isolate for the coefficients, and combine them in terms of n as well. And there we have it. Are you done, Fourier? We're done. So in its full glory, the Fourier series. I mean, right now it looks so incredibly mathematically complicated, but we derived all of it ourselves. And remember where we got it from? From heat flowing from hot to cold. That is just crazy how far we reached with just that and some insane logic. Oh, wow. That is just wow. So now that we know exactly how to figure out the frequencies and the heights, we can test it in our simulation. And the result is right in front of us. Indeed, any random signal can be built using sine waves, even ones with the sharp corners. Ideally, we need infinite components, but the more we add, the closer we get to it. Gosh, this is awesome. There's one loose end left though. Remember how we assume that our signal repeats forever? But real-world signals don't. So again, Fourier, I think it's going to be hard to translate everything that we derived to the real world. And Fourier says, actually, Mahesh, super easy. Barely an inconvenience. What? How? Non-periodic signals can be thought as periodic signals with period infinity. Oh, that is so brilliant. What a brilliant logic. Non-periodic signals are periodic with infinite period. That is so brilliant. You gotta love mathematicians, man. Come on, that is cool. Okay, let's calm down. Because when you do, you realize that's a big problem. See, if the period goes to infinity, the heights all go to 0. Everything goes to 0. The whole thing breaks. Fourier says, Mahesh, that's not a bug. That's actually a feature. Let's go to infinity step by step. Let's start with the period t. If we double the period, the heights all get halved, right? Because there's a divided by t. But now more frequencies are allowed to squeeze in between. So although the heights got halved, the number of components doubled, and that compensates. Double the period again, the same thing happens again. As the periods get bigger and bigger, each individual components get shorter, but more and more frequencies get squeezed in. And in the limit where the period goes to infinity, the heights of individual ones shrink to 0, but the frequencies themselves becomes a smooth, continuous spectrum. So now we have the full picture. For a periodic signal, we get discrete set of frequencies, and we can add them up as a Fourier series. But when we have a non-periodic signal, we no longer have separate countable components. We have a whole continuum of frequencies. So this goes away, and the heights and the phase shifts become functions of frequency. This is called a Fourier transform because we have transformed the signal into a frequency domain. And this reconstruction is no longer a summation, but it's an integral. And that is what we call an inverse transform because we're going back. And yes, this does look complicated and I may have glossed over some of the details, but the central idea is the exact same. Fourier transform breaks any signal into its constituent frequency components, and the inverse transform just adds them back together. At this point, I thought that this Fourier's idea with all this math wouldn't have any real application until the digital era. I was wrong. For most of human history, trade, travel, and war depended on ships, and ships are vulnerable to tides. Miscalculating tides could mean your ships run aground or even sinks. But wait, aren't tides easy to predict? The moon causes 2 high tides and 2 low tides per day, right? Well, mostly yes, but the exact heights and the times change significantly from day to day, making it hard to predict the future. But why does this happen? Well, because moon only produces one major contribution. There is also the sun, which produces another contribution with a slightly different period. And the moon's changing distance and angles introduce more and more such components. So the tides we actually see eventually is all of them added together. Now, the frequency of these components is something that we know. It comes from astronomy. But what about their heights? And what about their exact phase, which definitely affects the tides? These depend on the details, the nooks and the crannies of the local coastline, which is practically impossible to calculate. So at any given location, how do we find the heights and the phase of each component? Fourier! William Thomson, who later became Lord Kelvin, realized he could take historical tide data from any location and use Fourier's analysis to extract the major components. Then simply extend those sinusoids into the future and add them back together. Pretty similar to what Fourier initially did to solve the heat equation. Oh my god, that is pretty cool. So he and his brother built 2 machines, an integrator to extract the components and another one, a tide predictor machine, which adds those components back. A few hours of running these machines could predict an year's worth of tides data. This was a complete game changer. The British sea trade thrived because of this. And decades later, the Allies used a similar machine to predict the tides and plan their invasion of the German-occupied France. So what's crazy is that an idea which was developed to solve the heat equation ended up helping plan the biggest seaborne invasion in the history. You can't make this up.
The Allied armies were striking back.
And today this idea is used everywhere. For example, when I'm responding to my wife with a voice message, say, "Hey wifey, I love you too." My phone is not going to save the entire thing as is because it's going to take up a lot of unnecessary space. Instead, it breaks it down into its constituent frequencies. Now, of course, this is a Fourier transform, so there will be a continuum because it's a non-periodic signal, but never mind all of that. What's important is that a lot of these frequencies, like very high, very low frequencies, or the ones that have very feeble sound, the human ears can't detect them anyways. So there's no point in keeping them. So we can get rid of a lot of that useless information and only keep the ones that matter. So we'll only save the information of the frequencies that matter, and that will take up a lot less space. That's how audio compression works. It's an oversimplified version, but that's basically it. And now when I send this to my wife, her phone will basically reconstruct that message by adding those frequencies together. And if everything works well, that message will sound identical. "Hey wifey, I love YouTube." Oh, crap. The same idea works with photos. A photo is basically a grid of pixels, which can be thought of as a signal, a brightness signal. Of course, this should be a 2-dimensional signal, but I'm just representing it as 1D. Again, oversimplification. But the idea is the same. If you try to store it as is, that's going to take up a lot of unnecessary space. Instead, break it down into its constituent frequencies, get rid of the ones that our eyes will not be able to detect anyways, and then just store the information of the ones that matter. That will take up a lot less space. That is image compression. And then when I double click and open that photo again, it's going to reconstruct that image from those constituent frequencies, and my image is pretty much going to look the same. The same idea works with videos. And think about removing noise from audio or blurring and sharpening photos. It's all about just fiddling with the right frequency components. Fourier transforms are used in Wi-Fi's, MRIs, radars, you name it. Finally, just like how a prism physically separates light into its constituent colors, I was wondering, could we build something similar for sound? Turns out you can. Just play the sound near a row of tiny oscillators of different lengths. What do you think will happen? Well, the short oscillators are pretty stiff, so they only respond to high frequencies. But the long ones are quite flexible, so they respond to low frequencies. So depending on the frequencies that make this sound up, different oscillators will start getting driven. So look, which ones vibrate tell us which frequencies are present, and how strongly they vibrate tells us the strength of each one. A physical Fourier analyzer. And this is kind of how our ears separate frequencies. I kid you not. The cochlea, which is part of the inner ear, has a similar setup. One end is stiff and it responds to only high frequencies, whereas the other end, which is the apex, is quite flexible and that responds to the lower ones. And so depending upon which ones vibrate and how strongly they vibrate, they get converted into the electrical signals that get sent to the brain. This is one of the first steps that lets our brain distinguish sounds and understand speech. So although it took us a while to get to a point where we understand Fourier transforms, our bodies have been doing it since we were born. That's pretty awesome. I'll see you. Special thanks to my top patrons. You folks are truly, truly awesome.